Okay, so we need to finish curvature and then move on. There's one more curvature formula. So I gave you a few different ways yesterday to calculate curvature. Another way, this is the curvature in terms of x. So this one is not using t, this is using x. In the numerator, you take the second derivative of f with respect to x, take the absolute value of that. Denominator is the quantity 1 plus the first derivative of f with respect to x, that's squared, that whole quantity to the power 3 over 2. So this curvature formula, you're not going to use a whole ton. You're going to use it, though, when you have a function in terms of x. So if I give you a function in terms of x instead of parametric equations, this is the formula that you're going to use. So next example, we are going to find the curvature of the parabola y equals x squared at the points 0, 0, 1, 1, and 2, 4. In this case, our y, which is really f of x, is going to be equal to x squared. Our first derivative with respect to x then would be 2x, and our second derivative would be 2. So we're going to find a general expression for the curvature, and then we'll plug in those points. Curvature then is the absolute value of the second derivative, which in this case is 2, divided by 1 add the second derivative squared, all to the power 3 over 2. Simplifying that, we get 2. In the denominator, 1 plus 4x squared, all to the power 3 over 2. Okay, we have to plug in these points. At the point 0, 0, that's where x is 0, so you would plug in a 0. If you do, you get 2 divided by 1, so the curvature at the point 0, 0 is 2. If you plug in 1, you get 2 divided by 5 to the power 3 over 2, which I will tell you is about 0.018. If you plug in 2 into this general expression, you get 2 divided by 17 to the power 3 over 2, which is about 0.03. So you guys see I'm just plugging in the x values. One thing for us to notice is if we take the limit as x goes to infinity, the curvature is going to go to 0. And we're going to look at graphically what that means. So what I want us to do real quick is let's sketch the parabola, and then let's sketch the curvature function. So this is just our regular parabola of y equals x squared. Now if we want to plot this curvature function, when x is 0, we get a curvature of 2, so that's up here. When x is 1, we get a curvature of 0.018, so something really small like that. This ends up being what the curvature function looks like, except not actually hitting 0. It should just be approaching 0. So you're not going to graph the curvature functions very often, but it's interesting to see. We see here at the vertex of the parabola, that's when the curvature is highest. As you get further away from the vertex, that's when the curvature is low. And that should make sense. When we look up here, the tangent is changing very slowly. Okay, how do we feel about curvature? Fine? Okay, great. There's one other thing that relates to curvature, and that's called the radius or the circle of curvature. So the radius of curvature that symbol right there. Do you know what symbol this is?
Rho.
This is rho. Okay, so the way to find radius of curvature, and this should make sense, is 1 divided by the curvature. That should make sense because of the circle example we did yesterday. Yesterday, with the example of a circle, the radius was a, and we got a curvature of 1 over a. That's where this comes from. Okay, so yesterday we said the curvature of a circle is 1 over a, and we talked about as a increases, the curvature goes down. Same thing here, as the curvature increases, the radius gets smaller. Okay, so if we look at number 6 again, if we sketch the parabola out again, we're not going to sketch the curvature function, we're just going to sketch the y equals x squared. Okay, we are going to specifically focus at the point 0, 0. So we already said at the point 0, 0, the curvature was 2. That means then that the radius of curvature at that point is 1 over 2, because it's 1 divided by the curvature. Okay, so this is what that tells us. At the point 0, 0, the curvature, whatever the curvature is the same curvature as a circle with a radius of 1/2. So if we had a circle that had a radius of 1/2, it would have the same curvature as this function at the point 0, 0. So then what you often do is you'll draw in the radius or the circle of curvature. Circle of curvature is a circle with that radius. So starting at this point, that would be the circle of curvature. So it's a circle with a radius of 1/2. And you'll notice down here, they're going to have the same curvature. Okay. That is all things curvature. Sound good? Great. I'm going to tell you right off the bat, the next thing we're doing is not difficult, but it's tedious. So just note that. Next thing we need to talk about is there's a few more important vectors. First one is called a normal vector. Second one is called a binormal vector. First important vector we already talked about, and that's the unit tangent vector. So that was big T of t. That was equal to r prime of t divided by the norm of r prime of t. The importance of the unit tangent vector is that it points in the direction of increasing parameter. So that's the first one, the unit tangent vector. We already talked about that one. You also have a unit normal vector. So this is one that's new. Unit normal vector is going to be n, big N. Okay, the unit normal vector is going to be when you take the derivative of the unit tangent vector, and then whatever you get, you make it a unit vector again. So this will be t prime of t, so taking the derivative of your unit tangent vector and then making that result a unit vector. Okay, so one thing that this points out to us that's very important, if this is a unit vector and you take a derivative, it's not necessarily still a unit vector. So you do need to make it a unit vector again. Here's the importance of the unit normal vector. It points inward towards the concave part of C, C being your curve. So let's say that this is our curve C. Now let's say this is the point that we're looking at. So the unit tangent vector, let's say this is our orientation. Unit tangent vector is going to be tangent to the curve at that point, and it's going to point in the direction of increasing parameter. So this would be the unit tangent vector. Unit normal vector, if I take the derivative of a vector, the derivative is going to be perpendicular to my original vector. So these two are going to be perpendicular. This points towards the concave part of C. So that would be this direction. So unit tangent vector, unit normal vector are always going to be perpendicular. Last vector is called the binormal vector. Okay, binormal vector is going to be a vector that's perpendicular to both the unit tangent and the unit normal vector. So if I have two vectors, how do I find a vector that is orthogonal to them? Cross product. So the big B is the binormal vector. That's going to be the unit tangent vector crossed with the unit normal vector. Now, one thing to notice, this will always be a unit vector. So with the binormal vector, you don't have to worry about making it a unit vector. It's always going to be a unit vector, and here's why. If I take t and n and cross them and take the norm, if you remember, that's the same as the norm of t multiplied by the norm of n times sine of theta. In this case, t and n are always perpendicular, so theta would be 90, sine of 90 is 1. So this is a unit vector, this is a unit vector, hence that has to be a unit vector then. Does that make sense? You guys with me? Okay, great. Example. R of t is 3 sine of t, 3 cosine of t, and 4t. We are going to find all three vectors, the unit tangent, the unit normal, and the binormal. We are going to start by finding the derivative of r. Derivative of 3 sine is going to be 3 cosine of t, and then negative 3 sine of t, and then 4. If I want to find the norm, can I trust that you guys are okay finding the norm on your own and we don't need to go through it? Okay, you should be able to tell me, though, looking at it, what it is. 5. If you can't do it long ways, that's fine. So then the unit tangent vector is going to be r prime divided by the norm. So it'll be 3/5 cosine of t, negative 3/5 sine of t, and then 4/5. If I want to find the unit normal vector, then I'm going to have to take the derivative of the unit tangent vector. So this will be negative 3/5 sine of t, negative 3/5 cosine of t, and then 0. Is this a unit vector? No. Can you tell me what the norm is? I know you know how to do the whole work to find it if you had to, but can you tell me by looking at it what it is? Just plain old 3/5. And again, you could square them, add them all up. That's fine. So the unit normal vector then is going to be when I take t prime and divide by its magnitude. So I get negative sine of t, negative cosine of t, and then 0. Next one we need to find is the binormal vector. That's going to be when I take the unit tangent vector and cross it with the unit normal vector. So I get 3/5 cosine t, negative 3/5 sine of t, 4/5, and then negative sine of t, negative cosine of t, and 0. Bless you. Okay, so in this case, I'm going to multiply this way and subtract multiplying by that way. So I get 4/5 cosine t. Here I get 0 minus negative 4/5 sine of t, but remember with j, you flip the sign. Here with k, I get negative 3/5 cosine squared t minus 3/5 sine squared t, which is negative 3/5. So that would be our binormal vector. Now remember, the binormal vector is always going to be a unit vector, so we don't have to make that unit, it already is. Okay. Questions? No. Great. Here is one other way to find the binormal vector. Other way to find the binormal vector. In the numerator, it's going to be r prime of t crossed with r double prime of t. And then the denominator is going to be the magnitude of that vector. So that's very similar to what we just did. You need to know this formula. I'm never going to tell you to use one over another, though. Okay. We're doing pretty good, guys. We only have a few other examples to do. Ready to keep going? Okay, we're going to do one more example like this so that I can show you some ways to make this a little bit more efficient. Okay, let's say that our r of t is t, comma, root 2 over 2 t squared, comma, 1/3 t cubed. I want us to find the unit tangent vector and the unit normal vector at t equals 2. Okay, so the example we did before, this example 7, we found all the vectors, we didn't plug in any value of t. So that's what I'm asking you to do here. Find the unit tangent, find the unit normal, and plug in t equals 2. So in this case, we're going to get a vector with numbers that doesn't have any variables. So let's start with the unit tangent vector. We're going to need to find r prime of t, which in this case is 1, root 2t, and then t squared. And we need the magnitude of that vector. This will be 1 plus 2t squared plus t to the 4th. Hopefully you can see that that factors to be t squared plus 1 quantity squared. So that then tells us that our magnitude is t squared plus 1. Our unit tangent vector then is going to be r prime of t divided by the norm. So we'll get 1 over t squared plus 1, comma, root 2t over t squared plus 1, comma, t squared over t squared plus 1. I, though, asked you for the unit tangent vector at t equals 2. So you're going to plug in 2. When you do, you get 1/5. 2 root 2 over 5, and 4/5. Okay, questions on that one before we do unit normal? Okay, unit normal vector then. Okay, as a recollection, we need to take the derivative of the unit tangent and then divide by the norm. Can I start with the unit tangent at 2? No. What's going to be the problem if I do that? I'm just going to get all zeros. Okay, so I need to go back to here and find the derivative. Okay, do you see that that's going to end up being not so nice?
Yes.
Okay, well, I don't have any way to make that easier, so we actually have to do it. I'm sorry. Okay, so we're going to get negative 2t over t squared plus 1 squared for the first one. Second one, we're going to have to do quotient rule. So we get root 2 times t squared plus 1 minus root 2t times 2t all over t squared plus 1 squared. And then here we're going to have to do the quotient rule again. We get 2t times t squared plus 1 minus t squared times 2t all over t squared plus 1 squared. So that ends up being negative 2t over t squared plus 1 squared. If we look here, can I just tell you what it ends up being? You okay with that? It ends up being negative 2t squared add root 2 all over t squared plus 1 squared. Here we get a 2t squared minus 2t squared, so we're just left with a 2t divided by that t squared plus 1 squared. Whew. Okay. What do we need to do next? Okay. What we did before is we found the magnitude of this, right? Okay. That is not the most efficient way to do this. You can certainly go about that. An easier way is you can now plug in 2. So you can plug in 2 and then find the magnitude of the resulting vector. So if we find t prime of 2, when you plug in 2, I'll tell you, you get negative 4 over 25, negative 8 plus root 2, that quantity divided by 25, and then 4 divided by 25. Now you can find the magnitude. It's easier to find the magnitude of this vector than it is to find the magnitude of that vector. Oh, that's what we got to do next. So we get 16 over 625. Remember, when you're squaring that, you're going to have to FOIL or multiply the binomial correctly. Don't distribute the squared. So you'll get 64 minus 16 root 2 plus 2, all of that over 625. Plus 16 over 625 again. That ends up being the square root of 98 minus 16 root 2 all over 625. Keep the square root in the numerator. Denominator, that'll be 15. I am perfectly okay with you leaving it like this. Okay, so I'm fine with the square root and the square root again. So our unit normal vector then at 2.
Shouldn't that be 25, isn't it?
Yes, thank you. 25. Unit normal vector will be this vector divided by this magnitude. So, you see that the 25s are going to cancel each time. So we get negative 4 divided by the square root of 98 minus 16 root 2. Then we get negative 8 plus root 2 divided by, bless you, the square root of 98 minus 16 root 2. And then 4 divided by the square root of 98 minus 16 root 2. And that's our unit normal vector. I initially was going to have us find the binormal vector too, and then I got to this point and I was like, no, not going to happen. Okay, at this point, do you see that if you found the binormal vector, you could cross these two? That you're okay plugging in t equals 2 before you cross? We're not going to, but I'm just telling you, when you're doing these questions, think about when you're allowed to plug in 2 and when you need to wait. If you could plug in 2 early, plug it in because it'll make things much easier. Man, look at us go. We're doing so good. Okay. Ready to move on?
Yes.
Yeah?
Yeah.
Okay, great. Let's consider that we have this curve again, C. I don't know why I made it dotted line, but just go with me. Okay, and let's say we're looking at this point here. Whoa. Okay, we already said we have some unit tangent vector. The unit normal vector is going to be perpendicular to the binormal, or to the unit tangent vector, and it's going to go in on the concave part. Then we talked about if we cross these, we're going to get the binormal vector, which is coming out at us. Does that make sense? It's like really coming out. Okay, next thing that we are interested in is writing the equation of a plane. So we might be interested in the plane that is determined by the unit tangent and the binormal vectors. So that plane is the plane that is determined by the binormal and unit tangent. How many of these planes exist, or how many planes can we find the equation of here? 3, right? The binormal and the unit tangent and the unit normal, etc. Those all have specific names. If I find the plane that's the unit normal and the binormal, this is the easiest one to remember, at least. It's called the normal plane. What's important about the normal plane is it's the plane that has all lines that are orthogonal to t. So if for some reason you wanted the plane of all the lines that were orthogonal to the unit tangent, you would find the normal plane. If you take the unit tangent and the unit normal and find that plane, that's called the oscillating plane. Congratulations. This is the first time you want to know? Every other topic you thought was useful to you? But this is where I lose you, is the equation of a plane. We already found equations of planes. Do you not like the name? Okay, oscillating plane is related to the circle of curvature. Or the oscillating circle. These are all fun facts. I'm not going to ask you them. You do need to know the words, though. I will say find the equation of the oscillating plane, and you need to know which plane that is. If I do the unit tangent and the binormal, like the one that I drew in. Greta, do you know this one?
No, sorry.
Disappointed. That is called the rectifying plane. Okay, so since we're all so excited to find the equations of these planes, we're going to do an example. Before we do, when you are finding the equation of a plane, what 2 pieces of information do you need? Normal vector and a point on the plane. Okay, what example is this? 9, thanks. Okay, we are going to find the equations of the normal and oscillating planes for example number something. Which was the example that was r of t equals 3 sine t, 3 cosine t that we did today? 7, great, for example number 7. Okay. So we have to find the normal plane first, or I guess it really doesn't matter which one we find first. That is the normal vector and the binormal vector. So like we said, we need a point, and we need a normal vector. How do I find a point that is on this plane? To where? Okay, good. Oh, I didn't tell you at what point. Whoops! You guys should have been telling me we can't find a point, because you need to know what point we're looking at. So it's at the point 302 pi. So look, I just did the work for you. The point is 302 pi. Whew. Okay, how do we find the normal vector? So a vector that is normal to the unit normal and the binormal vector. Which vector is perpendicular to both of those? The unit tangent vector, yeah. What value am I going to be plugging in? Might be helpful if I reminded us what this is. Is it 3 sine? Did 3 sine come first?
Yeah.
Okay. So how do we know what value of t to plug in? Yeah, look at, is it 4t? Okay, how about that? Okay, so if we set 4t equal to t to 2 pi, we get t to be pi over 2. Plug that into x and y, and sure enough, you do get 3 and 0. So if we plug in pi over 2, you guys have the vector already written, but if you plug it in, you should get 0, negative 3/5, and 4/5. Yeah, good? Okay, great. So we get 0 times the quantity x minus 3, and then negative 3/5 times the quantity y subtract 0, positive 4/5 times z minus 2 pi, all of that equals 0. That's the equation of the plane. That goes away, so we get negative 3/5 y plus 4/5 z, subtract 8/5 pi equals 0. It's fine if you leave it like that. It's fine if you move the 8/5 to the other side. Okay. Do we get the point of these planes? Well, not why to use them. No. I'm sorry. That was a silly question. Do we understand how to find them, even though we don't see the use of them?
Yes.
Okay, great. I would love to be able to tell you how they're used. I don't think anyone uses them, though, if I'm being honest with you. Yeah, the unit tangent vector that we found before.
Oh, that we already found. Do you have a fun fact for rectifying plane?
I do not. I'm sorry. So we're good? Great. We have one other example to do, and then we're done with notes. So excited for us. Yeah, we're not going to fly in the osculating because you guys get the point, right? Not the point. You understand how to find them. You okay?
Yeah.
Okay, let's consider this ellipse. The ellipse that is given by the equation r of t is equal to 2 cosine of ti add 3 sine of tj. And we're saying that t is between 0 and 2 pi. Okay, if I asked you to find the curvature, could you? Based on one of the many formulas I've given you. Okay, so are we okay if I just tell you what the formula is?
Yes.
Great. Or now what the formula is, what the curvature ends up being. Curvature ends up being, in the numerator, 6. Denominator, the quantity 4 sine squared t plus 9 cosine squared t, that whole quantity to the power 3 over 2. If you don't trust me, you can do it on your own, but I think I'm right. So, we're going to draw or find, whichever word you want to use, the osculating circles at the point 2, 0 and the point 0, negative 3. When I say osculating circles, I mean circles of curvature. So we're doing that again. Okay. I went 7 in each direction on my grid, so that's what I would suggest you do. Okay, if we draw this ellipse, plug in 0, pi, 2 pi, etc. If you plug in 0, we get 2, and then 0. So that'll be this point right here. If we plug in pi over 2, we get 0, 3. So you should be able to see that this is what your ellipse is going to look like. Okay, with me? If we go to the point 2, 0, and we find the curvature, if you plug in at this point t equals 0, and just trust me, you get a curvature of 2/9. That tells you that the radius of curvature then is 9 over 2. So at this point, the curvature is the same as a circle that has a radius of 9 over 2. With me? Okay, so what you're going to do then is you need to draw in a circle with a radius of 9 over 2. Starting here, that just means the diameter is 9, so it goes all the way to here. So that is our osculating circle, or our circle of curvature. This circle and this ellipse at that point, 2, 0, have the same curvature. Other one we were looking at was 0, negative 3, so that point right there. If you plug in 0 and negative 3, so that's really 3 pi over 2. If you plug 3 pi over 2 in there, I will tell you that the curvature ends up being 3/4. That tells us that the radius of curvature is 4 over 3. So then we're drawing a circle here that has a radius of 4/3. Which is about there. So that was just another fun osculating circle problem. Do we have any questions about this section?
Why'd you plug in like t equals 0 to find the curvature of 2/9? Why not?
Of 2, 0?
Did you just plug in t equals 0?
Mm-hmm.
How? Why?
Because t equals 0, when you plug it in here, will give you this point.
Oh, okay.
Anything else from this section as a whole?